So we're gonna take a look into them, see what they are, why we need them, how they work, and the different variations between them. And if you happen to be new to blockchain technology and want to get a basic understanding of what blockchains are, you should definitely check out my previous episode called Demystifying Blockchains, which goes over the fundamentals and the underlying technology. Now, into today's episode. One of the key issues when using decentralized networks and protocols is that we don't necessarily trust the other people who are also using the network. When we use an application to buy or sell coins or tokens, we don't know who the person on the other side of this transaction are. To us, they are anonymous. We have no way of knowing their intents, whether they're trustworthy or not, and in most cases, we don't even get a public address of the person we're interacting with. This raises the question, how do we know that the person we're working with is trustworthy? Or more generally, how can we trust anyone on the network without knowing their true identity? And this is where consensus algorithms come into play. They use the idea that if a large majority of participants agree on something, then it must be true. Each protocol varies how they measure a majority. For some protocols, the majority is 51%, and although the theoretical limit is 100%, having a consensus protocol which requires agreement by the entire network probably wouldn't get very far or would be extremely slow. This is because we can generally accept some natural disagreement due to parts of the network becoming temporarily isolated or due to other reasons. In many cases, the nodes in the network, who are those participating in the network, propagate their votes towards the other nodes, making their viewpoint visible to others. And once they receive enough votes from other nodes regarding their viewpoints, a node can be confident in its decision regarding the state of the network. However, this raises another problem. If there is an almost infinite amount of addresses for any given cryptocurrency, how can we prevent a single user from creating a large number of identities to push the network in their favor? This is what's known as the cyber attack. And the solution varies from protocol to protocol. But the general solution is that to become a validating node in the network, there is a cost or investment required. The larger the requirement to participate, the less likely it is that there will be malicious participants. We'll discuss how the protocols approach this problem as we discuss them. The first consensus algorithm we'll discuss is proof of work. Proof of work was one of the first accepted consensus protocols, which has widespread adoption in the cryptocurrency space. It was introduced through Bitcoin as a way to ensure actors participated fairly and in a trustworthy manner. Proof of work requires validators. Again, validators are those who will take transactions and append them or write them to the blockchain. It requires the validators to carry out a number of complex mathematical equations, and these equations are built such that given an answer or a claim, anyone else can trivially check the answer. And if the given answer is correct, that particular validator will append or write this data to the blockchain and will generally receive some reward for it. And this reward is paid out in Bitcoin. To participate in proof of work, there's a small technical barrier to entry, but this is trivial for most devices. The largest barrier to entry is the computational capacity of the hardware. Most general use computers will not be able to compete with specialized hardware, and most competitive miners are using extremely specialized hardware, and this hardware was made for partaking in the Bitcoin network. However, there are also some components which are available to most other people. These are the GPUs or graphics processing units, which are often used in many computers. These can be used to partake in the proof of work protocol. And another benefit of the proof of work protocol is that we can actually pool together our resources with others to become more competitive. So that means you and many others across the internet can all work together and then take a share of the rewards from partaking in proof of work. While we are discussing proof of work, we should also discuss one of the largest criticisms of proof of work, which is its power usage, as computers are expected to run around the clock to carry out these computations. Personally, the validity of these arguments varies, and it kind of belongs in an episode in its own. That being said, electricity costs is one of the most important factors for validators when participating in proof of work. if their costs exceed the expected revenue of the tokens or coins they earn, they probably shouldn't be partaking. The next set of consensus protocols that we'll discuss are proof of stake and delegated proof of stake. So proof of stake is a development which was made on proof of work, aiming primarily to reduce energy consumption by selecting a validator before proposing transactions to be added to the blockchain. This differs from proof of work, where in proof of work everybody is competing against each other, whereas in proof of stake an individual is chosen and only they are expected to carry out these calculations. So in a system which implements proof of stake, choosing the validator is done in what I would call a economically democratic way. The chance of being a validator is proportional to your stake against the total number of tokens being staked. For example, if I staked 10% of all tokens in circulation, I would have a 10% chance of being chosen as the validator for the next set of transactions. Delegated proof of stake is an adaptation of proof of stake. Here, users can run as validators using their own tokens as a stake, but can also allow other users who may or may not be eligible to become validators themselves to bond their tokens to that validator. This effectively creates a proof of stake consensus through a smaller number of validators. An example of this is on Binance Smart Chain. To become a validator, there's a minimum stake of 10,000 BNB required, and this is approximately over £2 to £3 million and over $4 million. And then from here, other users can bond their BNB to certain validators to also earn staking rewards. Binance Smart Chain also has a restriction that only the 21 validators with the high stake can validate at a given time. Another feature of proof of stake, which some implement and some do not, is called slashing. If a node is found to be acting maliciously or otherwise non-cooperatively, the protocol can withhold some of their stake as punishment, and in some cases prevent them from partaking in the consensus for a certain amount of time. For the next set of protocols, I'll be grouping together two sets of protocols since they operate in a similar way. These are Gossip and also Byzantine Fault Tolerance, or BFT. Both of these aim to prevent malicious or non-cooperative actors in the network through a series of short, and in some cases randomly chosen group conversations, where a number of nodes algorithmically discuss new transactions and share views of the network. After a few rounds of conversations, which can vary between implementations, a consensus is generally achieved. For some implementations, such as Avalanche, nodes also keep a memory of their past interactions, for example, which nodes have acted genuinely or not, and use this as part of their voting algorithm. And again, to prevent cyber attacks, there's generally a minimum stake required to participate in these protocols. And for the final set of consensus protocols that we'll discuss today, I'll be calling them proof of capacity, which I'm using as an umbrella term for a number of different protocols such as proof of space or proof of space-time. And these are unique from some of the others we've seen in the sense that validating is done by committing storage capacity to the network in certain increments. For example, you can commit spare capacity of your hard drive to the network, and in return you'll have a chance to be chosen as a validator proportional to the amount of storage that you are committing. Some examples of these are Sia Coin and Chia. In particular, Chia resulted in a large demand for hard drives and SSDs because storage is relatively cheap compared to processing power, which attracts a lot of demand for these products. And although it's not super popular, it definitely has its use cases, especially in protocols which are focusing on file sharing and decentralized file storage. So we may see proof of capacity protocols pop up more in the future. And just to kind of bring this all together, each of these consensus protocols all aim to address the blockchain trilemma, which is an idea that a cryptocurrency can either be two of the following: secure, decentralized, and fast. Proof of stake builds upon proof of work to be faster and more energy efficient. Delegated proof of stake increases on speed but compromises on decentralization, and also by extension security. But that doesn't mean that proof of work is useless. Ultimately, the merit of the protocol is tied to the value that the specific network can provide. And that's all from me today. Consensus algorithms are really a fundamental part of blockchains and also decentralized networks, and they are literally constantly evolving with new adaptations, and there's so many that you can research them for days on end. As always, if anyone has any questions or comments, feel free to reach out to me on social media, and it will be good to hear from you. And until next time, goodbye.